We're going to talk about deformation of solids. So I want you to mute your mics. You can mute your mics because you're going to be disturbing us. So we're going to talk about deformation of solids. But the most important thing which I want you guys to understand under deformation of solid is one, we're going to talk about Young's modulus. Two, we're going to talk about Hooke's law. Those are the only things we have to understand under deformation of solids. Okay? But first, let me give you the recap of Hooke's law. So Hooke's law, whenever we're talking about Hooke's law, we're talking about the relationship which is there between the force and the displacement. So let's assume that we have a spring. So here is my spring. Now this spring, I'm trying to stretch. You know, when you are stretching the spring, you are using the force. Okay, so the force that you are using to stretch the spring is what we call the applied force. That force is directed in that manner. Okay, so the original position where the spring was, it is at this point, and at that point, at equilibrium position, x is equal to 0, because at that point the spring has not been stretched. So now, when you stretch the spring, then you want just to leave it. It will definitely want to go back to its original position. So its original position is what we call the equilibrium position. It when you leave the spring, you stretch the spring, you release it, the spring will always want to go back to its original position. That is the equilibrium position. The force that is pushing that object to go back to its original position is what we call the restorant force, and it is directed in opposite direction as the applied force. That force, we call it the restorant force. The distance from the original position to where the spring is now is what we call the x. Okay? Therefore, the restorant force is given by negative kx. Now, why are we talking about negative? So the negative comes in because we are not using the applied force. We are using the force that is in opposite direction with the direction. So the direction is moving in this direction. Okay, the displacement, the x, which is the displacement, it is moving in this direction in positive x-axis. Then the force that we are using, the force that we are calling the restorant force, it is moving in opposite direction to the applied force. It is moving in this direction. That is the restorant force. So the negative comes in because the force is moving in opposite direction with the displacement. So that's the reason why we always say that the restorant force is given by negative k times x, where x is the displacement, F is the restorant force, k is the spring constant. Does that make sense, guys? The reason why we have got the negative. So Hooke's law, what I've explained here is under Hooke's law. Hooke's law states that the restorant force and the displacement, they are direct proportion to each other. So the restorant force is direct proportion to the displacement. What does it mean? If I increase the force, the displacement will go up. If I reduce the force, the displacement will go down. So they are direct proportion to each other. They are direct proportion to each other. Okay, so I've told you to say do not share your screen. You are going to disturb us. So once you start sharing your screen, I'm going to remove you. I hope you're able to see my screen. I Are you able to see my screen? Okay. So that's the reason why we are saying that Hooke's law states that the resultant force and the displacement, they are directly proportional to each other, is coming from this relationship. Nothing more. But now, we'll come back to this principle when I explain more about deformation of solids. Okay? So now, allow me to go back to Young's modulus. So, what does K tells us? We are saying that K is basically the spring constant. But what does it tell us? So K is the spring constant. Constant. So K tells us how stiffness or loose the spring is. If the spring, you can just basically see here, if I make K as a subject of formula, or if the K value is greater, or I just do this, if the K value is greater, what do we expect? If the K value is greater, we expect that our spring is going to be stiff. If the K value is less, we expect our spring to be loose. Okay? So now, we know what K value is. So K is constant. Okay? You cannot manipulate K. So K is constant. But F and X, we can manipulate it. Now, we are going to look at the relationship which is there between this formula and Young's modulus, which I'm about to introduce now. Okay? So let's talk about Young's modulus. So what is really Young's modulus? So basically, when you're talking about Young's modulus, that's why I say it is basically the same concept with Hooke's law. So we are just talking about the elasticity in strength, okay, or how stiff or how loose that material is. Okay, for example, so when we're talking about Young's modulus, in some books, but in most cases, they are going to represent Young's modulus with just Y. So Young's modulus is given by stress divided by strain. Another definition of Young's modulus, you can say that it is the ratio between the stress and the strain. But let's first talk about what is this stress. This stress we're talking about is the same stress you know, guys. Okay? The same stress you know. Let's assume to say you have been given 5 assignments to submit for physics. You are supposed to submit, you have been given today, and you are supposed to submit tomorrow by 12 hours. Okay? You are supposed to submit tomorrow by 12 hours. You have been given 3 assignments, and each assignment has got about maybe 20 questions. So you are going to be stressed. I want you to relate what is happening here. You are going to be stressed. So when we're talking about stress, it's basically the same as pressure. If someone has got pressure, you can borrow money from someone and they are giving you pressure. At the same time, you're going to be stressed. So stress and pressure, they are basically the same thing. So I've given you an example to say you have been given an assignment. Let's say you have been given assignment today, maybe 8 hours. You are supposed to submit today 12 hours. You are going to be stressed. Why are you going to be stressed? It's because the force is just too much within a short period of time, meaning the area which is there is less. So you have got less time, but the force is just too much. So that is stress. So basically, when we're talking about the stress, we are talking about the force divided by area. Okay? We're talking about the force divided by area. Same as pressure. Pressure is also area, or is also force divided by area. As simple as that. So force is in Newton, area is in meter squared. Therefore, we can say that stress is in Newton per square meter. These are the SI units for stress. Okay. What of strain? Let's also go ahead and talk about strain. So strain is basically the change in length divided by L initial. Why are we saying the change in L divided by L initial? Let's assume that we have got a wire. So this is my original wire. So the distance from this point here to that point, I'm going to call it L initial. I apply the force and this wire is going to be stretched all the way to that point. Now this is my final length. The distance from the original here to where the final is what we call the change in L. The change in length has got different names. The change in length, it can be called elongation or extension. When they're asking to find elongation or the extension, they're basically asking to find the change in L. As simple as that. Any problem there, guys? Any problem there? Yes, Mwape. Okay. So that is the strain. Now I can clearly see that the change in L is basically L final minus L initial. Okay? But you are not going to be using this anyway. So the change in L, I want you to know that it is extension. At the same time, we call it elongation. So now I can derive the formula for the Young's modulus. So since we are saying that Young's modulus is stress is force divided by area, divided by this division here is the one that I've put now here. The strain is change in L divided by L initial. But if we think of it, this is in meters, also this is in meters. So meters and meters can cancel. Therefore, strain has got no units because they are both in meters. So they will end up cancelling each other. Okay. Then another thing that we have to take note here is Young's modulus will be equal to the force divided by area times, because division can change to multiplication and then we do the reciprocal of this. So it will be the L initial divided by the change in L. Then we can say that Young's modulus is basically the force times the L initial divided by area times the change in L. This is the general formula which you have to be familiar with for Young's modulus. But I told you to say we want to see the relationship which is there between this formula and the formula for Young's modulus. Now, you have got a question? If you don't have a question, you can just mute your mic. Please ask. The difference between strain, the difference between what, sir? The difference between, okay, so the difference between strain and stress is when we're talking about strain, we want to see the ratio between the change in length and the original length. What proportion is there between the original length you had and the new length which you have now after stretching it? Okay, So when we're talking about the stress, we are talking about the proportion between the force and the area. So when you're talking about the strain, you are not interested in the force and the area. You are just interested you are interested in the proportion of the change in length and the original length. So you want to see what ratio do you have between the new length which you have now and the original length. That is strain. Okay? So like I said, I want us to see the relationship which is there between the Young's modulus formula and the Hooke's law formula. F is equal to negative kx. So one thing we have to understand is that from this formula which we have just come up with right now, I want us to go ahead and make F as a subject of formula. So we have the Young's modulus is equal to F times this area divided by the change in L. So if we are to cross multiply here, making F as a subject of formula, it will be FL is equal to Young's modulus times area times the change in L. Then we divide both sides by L initial, even here by L initial. These two guys will cancel out and we end up having force being equal to the Young's modulus times area times the change in L. Then I divide this by this. Now I want you guys to understand one thing. Making force as a subject of formula, there are some things which can change and there are some things which cannot change. For example, the original length, we do not expect original length to change. That if the original length is 2, it's going to be 2, but you are going to have change in L, change in L. But change in L can change depending on the force you have applied. The Young's modulus is going to be constant. The area of that material is not going to change. Okay? So in most cases, you are going to be given radius, meaning that the area of that material is basically pi r squared. So take note of this. So if these three things cannot change, then I can isolate them to say the force is given by this guy divided by L initial times the change in L. What does it mean? It means that if these three things are not changing, then this is my K. So in this case, my K is the Young's modulus area divided by L initial. My X is basically the change in L. So that's the relationship which is there. So now the person who was discovering this, he noted to say there's a relationship between Young's modulus and Hooke's law. Because if you make F as a subject of formula in Young's modulus, you discover that you are going to have variables which are not going to be changing, which they are going to be acting as K. The change in L is the one which is going to be X. So that's the relationship which is there. I hope you have gotten something. Another interesting part about strain and stress is this part. Yes, you can ask. You can go ahead and ask. So if I have my graph here, then I go ahead and say this is point, I'll have this point, I'll have that point, I'll have this point and that point. So I'll call this point O, that point A, that point B, and that point C. So I have got stress in x-axis, or I have got strain in x-axis and stress in y-axis. So from point O to A, this line here obeys Hooke's law. Okay? It obeys Hooke's law. I can get any point and I'm going to get the same answer. It obeys Hooke's law. So at point A, when you reach at point A, that's what we call elastic limit. So this point is what we call elastic limit. When you reach at point B, that point we call it plastic limit. So this is limit. So that is plastic limit. And point C, we call it breaking point. So now we have first to know and understand what these things are. I'm going to give you an example. Let's assume that we have the spring, and this spring, I stretch it, I reach at the maximum point. If I reach at the elastic limit, the moment I release that spring definitely has to come back to its original position. If this is my original position, this spring has to come back to that point. When I stretch the spring, it reaches at the maximum point where I can stretch it. I release it, it will come back to its original position, meaning I've reached at the elastic limit. Elastic limit is a point where when you stretch the spring, when you release it, it is going to go back to its original position. At that point, you have reached at the elastic limit. A situation where you stretch the spring, when you leave the spring, it's not going to go back to its original position. At that point, you have reached at the plastic limit. I can give an example. If you have got a plastic, you try to stretch it. The plastic is not going to go back to its original position. Not possible. So this is what I'm trying to explain. You apply a lot of force to that spring. You leave it. It is not going. If it doesn't go back to its original position, then that spring has reached at the plastic limit. Simple, right? If you stretch the spring, if you apply excessive force, you stretch the spring. Now that spring breaks into two pieces, meaning you have reached at breaking point. So these three terms are very important. You have to know them: elastic limit, plastic limit, breaking point. Does that make sense? Does that make sense? Okay. So if it does, then we can also go ahead and also talk about it. When you are stretching the spring, like I said, I'm stretching the spring. If this is my original position, at original position we said that this is at equilibrium position. X is 0. From this point here to that point is my X position. So now you are applying the force, and the force that is applied force, then we are talking about the resultant force. We said that F is given by negative kx. That's what we said. Now, a situation where we know that where you have got force, if I take you back to semester 1 to work energy and power, I told you guys, and you have been watching my videos, I told you to say work is equal to the force times the distance. Now, in this case, we have got the force, which is the resultant force. Okay? Then the distance which we're talking about is the x. So work is equal to the force times the x. Now, when we are talking about Hooke's law, the work done by the spring, when you want to find the formula, we use calculus method. I'm going to take the integral both side. So if I get the integral both side, then this is going to be work is equal to the integral of F. I want to integrate this in terms of the displacement, which is x. So this x is going to change to dx. If I take you back to grade 12, you guys know that the integral of x dx is the power we increase by 1, so it's going to be x squared divided by the power. Not so. If I give you the integral, if I give you the integral of 2 dx, you know that it's going to be 2x plus c, which is the constant. So in this case now, I do know that the resultant force is given by kx. Then I'm going to replace F with kx. So you ignore the negative. So the work done by the spring will be equal to, where there is F, put kx dx. Now k is something that is constant, more like a number which is constant. So you can put now k outside. You can say k, the integral of x dx. So you are now integrating this in terms of x. So it will be k x squared divided by 2. So if I try to rearrange this, the work done by the spring is given by half kx squared. So if you find a question telling you to show that the work done by the resultant force is given by half kx squared, this is where it's coming from. But I have got two methods which I'm going to show you. This is the first one. I'm going to show you the second one. Okay? For example, if you go in the first throw sheet for semester 2, this is the first question. Another method that I'm going to show you is, if I've got a graph, if I have my graph like that. So now this graph, one thing we have to know is that in y-axis we are going to be given force always. In x-axis we are going to be given the displacement, which is in meters always. And then you have got the spring here. Now the work done when you have been given the graph. Yes, if I've got a question you can ask. Yes, James? Okay. So the work done, when we're trying to find the work done, you have been given the graph. The work done is given by the area under that curve. For example, if I'm trying to find the work done under this curve, that is the triangle. So then I have to get the area under the curve. Under the curve. But what is the area under this curve? So work will be equal to area. Now the area of the triangle is half BH. So this is B and this is H. So then I can say that work is given by half. B is X. I know that is the displacement, which is X. Then H is F. And then I can rearrange this and say this is the same as half. I start with that F. But we also know that F is equal to Kx. I can replace F with Kx. So F is equal to negative, or it's going to be Kx times again X, which is this one. X times X is X squared. So then X, the work done by the spring, is given by half Kx squared. So this one, if you write this one, they can give you more marks because it is making more sense. Even to you, it's making more sense. So this is how you can show that the work done by the spring is given by half Kx squared. Any question, guys? Any question? Yes, please. Mishek, you can ask, sir. F is the force, sir. Yes, sir. Yes, please ask, guys. Ask. No, no problem. This class is being recorded. After this meeting, I'm going to upload the recorded class on YouTube, and you're going to watch it. Don't worry. So you'll be able to catch up. Okay, I understand. I understand, maybe due to network, but that's not a problem because I've recorded the class. So you'll be able to watch the recorded class, and then if you are still behind, you can still get in touch with me. Is that okay? Okay, so before we continue, since some of you are behind, um some of you guys have not even created an account on our website. And I tell you to say, this website is going to help you a lot, especially semester 2. So if you go on our website there, I want to show you something that is going to help you for semester 2. Okay? So if you go on our website and then maybe you want to check out physics. So there are different courses. So you have to create an account. There are different courses here. We have mathematics, physics, biology, chemistry, even for the past papers. But the past papers for physics, I've not yet uploaded them in physics past papers. I think I'm going to do that after maybe tomorrow. But for now, everything I had to add them here in physics. So when you just scroll down using your uh, course outline, it starts from here. This is where semester 2 starts. Vibration and waves. So if you click here, you are going to find that we have got vibration and waves Hooke's law introduction. So we have tutorial sheet 1 part 1, tutorial sheet 2 part, or tutorial sheet 1 part 2, tutorial sheet 2, then the simple harmonic motion, tutorial sheet 2, tutorial sheet 3. I explained almost everything for semester 2. This is the first topic. Then there is a test which I created for you. Then I also made solutions. And that test, I'm going, when we meet next, I'm going to give you the test. You try it out. Then I'm going to give you the solutions. After that, you come and watch this video. I made the solution for the test already. Okay. So another thing, if you want to go to vibration and wave, there are also new videos. I made new videos separated just for you guys, vibration and waves. Then there's also sound, electric forces and electric field, electric energy and capacitance, then vibration and the sound wave past papers. So these past papers from 2018 to 2023, I solved them already. All of them, like you're going to find them, I solved them with I want you to understand each and every step. I solved including MCQ and section B. Let's see the sample here. For example, part 1. This part 1, this is the paper, the question from 20, it should be 2018. So I solved all of them, these ones. That's we need to say semester 2 is going to be bit easy for you if you are a bit smart, because everything is already there. Tutorial sheet has full topic videos are there. This question, if I give you from today's class, you'll be able to answer it, and I'm going to share it with you. Okay. Another thing which I want to show you guys, what I did was I got the questions from vibration to sound wave. What of the other part? So now I also got the questions from these other topics. I also answered them, and they are here. I even included to say question 7 2023 physics. All of them here, they are here. Okay. Then there are those people DF. You go here, there's a link here, open document. When you open document, I answered all the MCQs from 2020, from 2018. From 2018, I can show you from here. I answered the past papers from 2018 MCQ with the better understanding. I can even give you the sample. Let me show you the sample. So like for those guys who already paid, you'll be able to access what I'm telling you right now, because I'm going to add this link, I think, after the class. So I was also working out, I was working, it was this one. So I tried to work, I did two parts. This is the first part. Now the second part I'm not done. So what I did was all the past papers, what I did was this. For example, these are questions from 2018 to 2023 past papers. So what I did was I got this question, even including test. I got this question and then I answered it. So I said, this is the question here. Now the answer is C. But why is the answer C? I had to explain why the answer is C. So I made a lot of questions about, how many are they? I made a lot of questions, a lot of them, a lot of them, a lot of them, about 35. Then there's also a bunch of, that is part 2 now. Okay, so do you know that you can access these while you are still at home? You can learn with us at your comfortable, like you make your own timetable to say, okay, I'm going to be having physics at this time, I'm going to be having math at this time, I'm going to be having biology at this time. Biology past papers, we solved all of them. Chemistry past papers, we solved all of them. Physics past papers, we solved all of them. Mathematics past papers, we did not solve all of them, but we solved some of them. Get me right there. But we are still solving. Okay, so in case you want to get access to all these videos I'm showing you, you can just go on our website. If you want, you can pay using the website, but for now it's not. Yes, you can pay using website, but if you're having challenges to pay using website, you can still get in touch with me. And you guys, I know you have my number. If you don't have my number is just this 0767729927. Get in touch with this number. Thank you for your time. We are going to talk in the group when next we are going to meet. But if you are having personal questions, you can still inbox me. I'm okay with that.